Welcome back, everyone. This is CS 480/680, Introduction to Machine Learning, as taught at the University of Waterloo in fall 2024. This is lecture 12, and today we're going to be talking about expectation maximization algorithm, as well as Gaussian mixture models. Um, so to set this idea of, what is expectation maximization, I'd like to quickly revisit the kinds of problems that we've been solving in this course. Okay, so we've encountered problems where we were given some data. So for example, x1 was 1, x2 was 2, and x3 was 0. And then given knowledge that this was sampled, that those samples came from a normal distribution, our task was to estimate the mean of that distribution from which our samples came. And maybe we would want to sample some new data given that distribution, or maybe we're just trying to infer something about the population that we've gotten our samples from. But yeah, this is a problem that we're pretty familiar with. And so yeah, once we've determined what that parameter is, or given knowledge of what that parameter is, uh, then we could go ahead and actually generate samples, draw new samples from it. In which case, what is X3? What would we predict for X3? So these are problems that we're pretty familiar with. But today we're going to be looking at a weird kind of problem where we have to estimate, a parameter or potentially all the parameters while we're missing some part of the data set, or there's some knowledge that we don't even have about the data. And so yeah, we're going to be encountering a kind of more challenging problem today, where our task of estimating the parameters of the distribution is kind of obstructed by the fact that we don't actually have all of the information we need in order to perform that task like we could with maximum likelihood estimation. And so, yeah, how do we solve a problem like that, where we're missing a sample and the parameter at the same time? And so one thing we could do is simply start with an initial guess for our parameters. Say we start by setting the mean to 0, or assuming that it's 0. But then if that's the case, if that's our initial guess for the mean, then the most likely value for that missing data point, x3 in our case, that would be 0, because the mean of the distribution is 0, and therefore x3 being 0 is our best guess based on what we know so far. But if that's the case, then we could plug that guess for x3 back into our back into our empirical calculation for the mean. So going back from before, where x1 was 1 and x2 was 2, then we go 1 plus 2 plus 0, and divide that all by 3, and now we have a new estimate for the mean, which is 1. Then if that's the case, then our best guess for x3 would be 1, because that we have a new mean and therefore a new most likely value for x3. But now we need to update our calculation for the mean, which would give us 4 over 3, or 1.33, which in turn implies a new best guess for x3, which in turn implies a new best guess for the mean, and so on and so forth. And so what you should be able to discern is that the corresponding updates that we're making in this iterative process are getting smaller and smaller. So we started off with a relatively large jump of 0 to 1, and then we only had to move a third of a step, and now we're moving very little at all. And these are going to converge. So our parameters and this missing data, that's going to converge in the case where they're both equal to 1.5 in this case. And so this iterative process, this is really the heart of the expectation maximization algorithm. And so the high level idea is to alternate between estimating the parameters we're trying to learn and while filling in missing data along the way. And so crucially, it's going to be an iterative process where each step improves our parameter estimates based on our best guess for the missing information on the way to moving closer to an optimal solution. And so the EM algorithm is essentially maximum likelihood estimation, but we've got a kind of twist. So it lets us work even when lets us work effectively, allows us to estimate the parameters, but when we're missing parts of the data. And so the way this might manifest in practice is we might be missing like columns of our data, missing rows, completely unobserved variables. And so expectation maximization, or the EM algorithm, that's going to help us estimate the parameters that maximize the likelihood of the data, maximize the likelihood of the data that we do have while handling those missing pieces. And so today we're going to be getting into the details of how the expectation maximization algorithm actually works. So in the introduction, we talked about this really high level idea, this kind of 50,000 foot view, really just to get you thinking about the kinds of things or the kinds of frameworks we'll be encountering today. But we're going to take a closer look at the mechanics of the algorithm and walk through it step by step. And so we're going to start with a special case. So one of the most common applications of EM, specifically that of estimating the parameters of a Gaussian mixture model. And we're going to start off by approaching this problem from a heuristic perspective to build some intuition about how the algorithm, or about what the algorithm is doing, and to motivate it from a heuristic place to see why it's effective. Yeah, so the goal in this first part of the talk is to motivate the core ideas of EM in a way that feels approachable. But after we establish that intuition, we're then going to dig deeper into the math behind the EM algorithm and look at how it works a bit more generally. So while the concepts that we uncover in in the first part are going to align with this general case, we're not going to connect every detail between the two. And so by the end of the lecture, the goal is to not only understand how EM works for Gaussian mixture models, but to be in a better position to be able to apply it to other problems involving latent variables or hidden variables or unobserved missing data. All right, so let's start with a motivating example that shows why we need an algorithm like EM in a real data set. So in the left-hand side of the slide here, I've got a histogram that represents some data set. So let's say it's heights among people centered around some average. So there seems to be this seems to be a bimodal distribution. The data has two distinct peaks, and so this might reflect two subgroups such as biological males and females, which each have their own average height and their own spread. And so normally we'd be trying to fit a single Gaussian distribution to this data set, but this wouldn't capture the two distinct modes very well at all. And so instead, what we might want to do is model this data as a mixture of Gaussians, a mixture of two Gaussians, one for each of the two subgroups. And so to do that, we can think of our data as coming from two normal distributions, two separate normal distributions. One with one mean specific to the first group, and the other with a different set of parameters. And so the idea here is that we're going to think about the data that we observed as generated by two random variables. So random variable x1, that's going to be drawn from one normal distribution with a certain mean and a certain variance, and random variable x2 is going to be drawn from another normal distribution with a different mean and a different variance. And then we're going to superimpose those random variables to generate a new variable x using by introducing a new binary random variable delta. And so this delta is going that's going to decide which of the two distributions a particular observation came from. So delta is a binary random variable. It's going to take on a value of either 0 or 1. And so it's going to determine whether we sample from the first or the second Gaussian. And so the full random variable x is generated by first sampling delta. So it will either be 0 or 1. And then once we know that either the first or the second normal distribution is chosen to generate the observed data point. And then we're also going to have a parameter pi, which controls how often each Gaussian is selected. And so pi is the probability that the delta takes on the value of 1. And so if pi is large, we're going to sample more often from the second mode, whereas if pi is small, we'll see more samples from the first mode. So the structure gives us the flexibility to combine the two Gaussians in different proportions, and it's going to allow the model to capture the bimodal nature of the data. And so we call this setup a mixture of Gaussians. It lets us model data that has multiple underlying modes, something that a single Gaussian couldn't handle. Right, and so the way that, and then the probability density of a Gaussian mixture model can be combined using pi together with our expressions for the densities of the individual modes. Okay, so the function that we're working with, the probability density for a Gaussian mixture model for the data p of x. This says that the data comes from a mixture of two normal distributions, one weighted by 1 minus pi, and the other weighted by pi. And then, as we saw in the last slide, each normal distribution is defined by its own parameters, mean and variance. And so our task is to estimate 5 parameters. Now we need to know pi. We need to know the two means as well as the two variances in order to describe this distribution. Our task is to estimate the 5 parameters of this Gaussian mixture model. And so a natural way to approach this problem is through maximum likelihood estimation. And so we set up a likelihood function that gives us the joint probability of observing the data points in our data set. And this likelihood is a product of the mixture of densities over all observations, which allows us to express how likely it is to see the data given our current parameters. And then, as usual, since working with these products can be messy, we take the log of the likelihood function, which turns this product into a sum, which historically has been much easier for us to handle. But now this looks a little bit different to what we've been seeing in the past, because normally after taking the log, we'd expect to have a sum of logs, which makes it easy to take the partial derivatives with respect to each parameter. But in this case, now we've actually got the log of a sum, and that makes things a bit more complicated. And so the structure creates a major challenge because taking the partial derivative of a log of a sum isn't straightforward. And so that usual trick of setting the derivatives to 0 to find the parameters is not going to work so easily here. I'm not quite sure how to go about finding closed form expressions for the partial derivatives in this case. Don't really know what that looks like. But there's another problem that you might have suspected. And so even if we tried to simplify things, And let's assume that we already knew the variance and the mixing weights. Um, estimating that the remaining parameters, like the two means, could actually still be tricky. So let's say that all we had to do was figure out the two means. So we actually someone told us the variances and the mixing weight. And so in this case, we could actually plot the likelihood surface for all possible values of those two means, shown here in the middle. So on one axis, we've got mu1, and on the other axis, we've got mu2. And these lines here, they represent contours of equivalent loss. And so these darker, cooler colors, they represent sorry, not loss, but log likelihood. So these cool dark colors, they indicate low log likelihood, whereas these red lines indicate high likelihood values. And so what we can see here is that there's a clear symmetry in this surface. There's two maxima, two equally good solutions. So each peak corresponds to a different possible assignment of the clusters to the means. And so the symmetry exists because it doesn't matter which mode we call the first one or the second one. The likelihood is going to be the same in both cases. So for example, like the left, whether the left peak corresponds to cluster one or the other, the math doesn't care. And so as a result, we have two optimal solutions that are identical in terms of likelihood. And so this is what's known as the label switching problem. And so since the likelihood function can't tell us which mode corresponds to which cluster, the parameters actually become unidentifiable. And so this means that there's no unique solution. So the symmetry in the likelihood surface makes the problem challenging because we can't take derivatives, can't set them to zero and solve for the parameters like we normally would. And it's important to note that this issue arose in this highly simplified case where we actually knew the variances and the mixing weights. In more complex models where we would normally be interested in, the situation's only going to get worse. And there might be potentially many symmetric modes in the likelihood function. And so direct optimization is going to be hard in these kinds of models. There could actually be exponentially many solutions, and distinguishing between them is going to become a real challenge. Okay, so we seem to have hit a bit of a wall. So let's take a step back and think about what we're really trying to do here. And so one thing we could do, one way we could proceed, is to imagine we had access to some extra information. Something some piece of information we don't actually have right now, and kind of elevating ourselves to that oracle level status. And then from that vantage point, we could then ask, what could we do with that information? If we had just one extra piece of the puzzle, would it help us solve the problem? How could it change our approach? Okay, so let's imagine for a moment that we knew the sample assignments. So what I mean by that is that we knew exactly which data points came from which mode. So even if we don't know the parameters yet, just having this information about which point belongs to which group could make things a lot easier. So with that knowledge, we could introduce delta as an indicator to show which mode each data point belongs to. So for example, if delta were 0, we would know that the point comes from the first Gaussian, whereas if delta was 1, it would belong to the second. And then we can split we've essentially split the log likelihood into two sums, corresponding to the log of the densities for each observation, with the delta indicator variable. And then this second sum here accounts for the contribution of the mixing weights, pi and 1 minus pi, depending on the value of delta. So essentially, we're separating the influence of the density terms and the mixing weights into two distinct sums to make the expression easier to work with. And so this, this thought experiment, we can see that this simplifies things dramatically. Because if delta takes on a value of 0 for a given data point, the expression we're only interested in this term and this term here, and so this whole thing simplifies to this blue part for a given data point. Essentially focusing only on the contribution from the first Gaussian. But on the other hand, if delta is 1, we're going to ignore that first Gaussian entirely, and the equation collapses to this pink part here, corresponding to the second Gaussian. So this breakdown lets us separate the contributions from the two modes, and makes it clear how we would calculate each part. So okay, so once the trick is that once we know the sample assignments, estimating the parameters becomes totally trivial. So the maximum likelihood estimates for the means and the variances, mu1, sigma1, mu2, sigma2 squared, they're just the sample mean and the variance of the data points assigned to each Gaussian. So for the first mode, we would compute the mean by summing all the points with delta equal to 0 and dividing by the number of those points. So the first mean, we're just going to add up all of the points that belong to the set for which delta is 0. And then once we have that mean, we're then in a position to calculate the variance of the first mode. And then for the second mode, we do the same for the points with delta equal to 1. Yeah. And so, yeah, knowing the sample assignments also makes it easy to estimate the mixing weight pi. And so we just take the proportion of points with delta equal to 1. So that's how we determine how much weight to give to the second Gaussian. So in this case, pi would be equal to the total number of points with delta equal to 1 divided by the number of samples in the whole data set. And so, yeah, knowing the sample assignments allows us to look at the data. It reveals a structure in the histogram. So this is what the data might look like after we split it into groups. And so with the data separated by mode, we're free to compute the independent parameter estimates for each Gaussian, just like you would in the simpler cases with fully observed data. So the mean and variance of each mode are computed separately, and everything is empirical, straightforward, arithmetic based on the assignments. Right. So key takeaway: if we had the sample assignments, the problem would be easy. Now let's imagine another situation. This time we know the parameters of the mixture model. So that means we know the mixing weight pi, as well as the means and variances of both Gaussian distributions. So what can we do with that information? Well, if we knew the parameters, we'd have a clear picture of the model and could also compute the probability that any given sample came from one mode or another. For instance, with the parameters in hand, we could compute we could plot the probability density function, which is shown in red, the red curve in this plot. And so each sample represented by one of these purple dots, that's going to have some density under both Gaussians. And so with that information, so for example, this purple point here, that would have a high density under this first Gaussian, and then it would have a low density under the second Gaussian under here. And so with this information, we could then compare the densities for each point across the two modes. And so yeah, if using this equation here. And so if a sample has a higher density on one Gaussian than another, we'd have a good idea that that it most likely came from that mode. And so the exact probability that a point belongs to the second mode is the density of the second Gaussian divided by the total weighted density across both modes. So we're essentially normalizing across all possibilities down here. And this quantity, the probability that a point belongs to the second mode is known as gamma I, or the responsibility of mode 2 for observation I. So in other words, it tells us how much responsibility a particular mode takes for generating a given point. We can think of this responsibility also as the expected value of delta I, which, as we saw earlier, was that indicator variable for whether a sample belonged to one mode or another. So knowing these responsibilities, that gives us a kind of probabilistic assignment to the clusters, even though we don't know the exact assignment for each point with certainty. So this green curve over here, that shows the values of gamma I, those responsibilities for the first mode across all of the samples. And so what we can see is that the points clustered on the left side here, the mode one takes most, if not all, of the responsibility, or most of the responsibility. But then as we move further to the right, the responsibility decreases, and the responsibility decreases. So points over here cannot be attributed to that first mode. And so, yeah, this isn't quite as clean as those nice those hard sample assignments that we might ideally like to have. But it's a way to quantify the likelihood that a sample belongs to each mode. So on the one hand, if we knew the parameters, we could compute the probability that each sample came from one mode or the other. It wouldn't be the exact sample assignments, but it would give us something close. Specifically a probabilistic assignment for each point. But then on the other hand, if we knew the sample assignments, we could easily calculate the parameters that maximize the likelihood. And this is because the empirical estimates, like the sample means and the variances, those are the values that maximize the likelihood function, as we saw in our lecture on maximum likelihood estimation. So could we, just combine these two somehow? Maybe iterate between them. Like what would that even look like? What would it look like to combine these two sets of partial knowledge? And so this setup is actually quite similar to Lloyd's algorithm that we saw for k-means clustering. And so with k-means, we had the same kind of challenge. We needed to assign points to clusters, but at the same time, we didn't actually know where those clusters were. And Lloyd's algorithm solved this by randomly initializing the partition, essentially assigning points to clusters at random just to get things started. But then from that starting point, the algorithm computed the centroids of the clusters based on the points assigned to each one. And then once the centroids were computed, the points were reassigned to the closest cluster based on the proximity to the new centroids. And so the process of recomputing the centroids and reassigning points that kept repeating, which gradually refined the cluster identities with each iteration. And then over time, that back and forth process allowed the algorithm to identify distinct clusters and assign points to them in a way that made sense. In this particular case, the clusters converged to spherical shapes, and the algorithm eventually stabilized when the assignments no longer changed. So this process of computing the centroids and k-means is a lot like estimating the parameters in our case. But yeah, how does our model compare with k-means? Like why am I drawing this connection to k-means exactly? And more importantly, can we map Lloyd's algorithm, or can we use Lloyd's algorithm as a kind of scaffold to approach this problem of parameter estimation for a Gaussian mixture model? And so in k-means, computing the centroids, that's a bit like finding the means of the Gaussians in our mixture. So each centroid in k-means corresponds to the mean of one Gaussian component. But in our case, the model's a bit more complex because in addition to the means, we also need to estimate the variances and the mixing weight for the Gaussians. And then another important difference is how we handle the assignments. And so in k-means, we had those hard sample assignments. So each point was assigned definitively to one cluster or another. But in the case of a Gaussian mixture model, the best we can do, given knowledge of the parameters, is to compute the probabilities of each point belonging to a particular mode. And so these probabilities represent the responsibility of each mode for generating a given data point. And this is a soft assignment. Essentially, it's to be precise, it's the expected value of the assignment variable for each point rather than a fixed binary decision. Yeah, there's some clear similarities between k-means and the Gaussian mixture model problem. Our model clearly involves more nuance. Yeah, could we adapt something like Lloyd's algorithm to handle the added complexity of Gaussian mixture models? So let's walk through this idea and see how it plays out. So let's randomly initialize the parameters of our Gaussian mixture model. Akin to the random initialization of clusters in k-means. So here we will be just picking the means, the variances, and mixing weights at random. And from that starting point, we'll use those initial guesses to compute the responsibilities, which are the probabilities that each data point belongs to a particular model. And as I said before, those responsibilities are captured by gamma, which gives us that sense of how likely it is that a given sample came from one Gaussian or another. And then once we've computed those responsibilities, the next step would be to update the parameters, the means, the variances, and mixing weights. And so in that case, we as you know, before we wanted to use the expressions for the empirical means, but separating the points based on their identities. But the problem is we don't have those hard assignments. We don't know definitively which mode each sample came from. So we can't just plug in the values like we could for the empirical estimate. So that's not going to work. And so instead of taking the empirical mean, where we sum all the data points and divide by the total number of points, we can apply weights to each point based on its responsibility. So for mode 1, for example, the weight for each point is going to be 1 minus gamma, and so that reflects how much responsibility that the first mode takes for that point. And then for mode 2, we can use gamma directly because that tells us how likely the point is to have come from the second mode. And so this way, every point contributes to the parameter estimates based on how strongly it belongs to each mode. And so, yeah, and then once we have the weighted means, we can move on to the weighted variances, where we're computing those weighted contributions to the parameter estimates in precisely the same way. And so uh, this approach, it ensures that points far away from a mode's mean, if they have low responsibility, they don't influence the estimates as much. It's unlikely that such a point that's far away from the mean, is likely to have come from that mode. And so we don't want that point to contribute. So the idea is that we don't want that point to contribute to the parameter estimates for that mode because it's unlikely to have come from it. On the other hand, if a point is very close to the mode, within the support of the distribution, if with high responsibility, those are going to be weighted more heavily, and that's going to give them more influence on the parameter estimates. But then we're also able to flexibly handle those intermediate cases where there's a point that, could have come from either mode. It's essentially a coin flip about whether it came from one mode or the other. And so those points, they're going to contribute to the parameter estimates for both modes. Although, not as much as those that have higher responsibilities. Right. So yeah, what we've done here is something that's intuitively motivated by the k-means algorithm. A similar iterative approach that alternates between sample assignments and parameter updates. But yeah, the real question is, does this work? Can this method reliably find parameter estimates? And so it turns out exactly what we just hacked together does converge. And so what you're looking at here is a plot from the elements to statistical learning text. And so on the x-axis, we've got the iteration number, and on the y-axis, that's we're tracking the log likelihood of the observed data at each step. And so as you can see, the procedure, it starts off with strongly negative log likelihood. It reflects the fact that our initial parameter estimates are quite poor, where the data was unlikely under those initial guesses. But then after the first iteration, that parameter estimate is refined. And we see a huge jump in the negative log likelihood, or in the log likelihood. And then successive iterations, we continue to see improvements, continually refining the parameter estimates. By the time we reach around 10 iterations, the curve has started to flatten out. So this signals that the algorithm has stabilized or converged. So by this 10 mark point, by 10 iterations, it's likely that we've found the correct estimates for all of our parameters. So in this case, that would be the means and the variances of both Gaussians as well as the mixing weight. So yeah, remarkably, within 10 iterations, we've managed to fit 5 parameters and align the model to the data. This convergence, shows that this approach we've taken, this algorithm inspired by k-means, it actually works well for the Gaussian mixture model. And so remarkably, this approach is precisely the expectation maximization algorithm for the specific case of applying it to a 2-component Gaussian mixture model with univariate Gaussians. The algorithm block that we're using here, this comes from the elements to statistical learning text. Just as we did, we start with making initial guesses for the parameters, the means, the variances, the mixing weights. There are some details in the text about how to choose these initial values carefully to ensure that the algorithm converges smoothly. But then once we have those initial guesses, we use them to compute the responsibilities represented by gamma. And those responsibilities, they told us the probability that each point belonged to one mode or another. And we need to compute them for every single data point independently, since each point can be partially attributed to either mode. In the text, the authors use phi to represent the normal density, and theta for the parameters of the distribution. But otherwise, the structure is exactly the same as our presentation. And so after computing these responsibilities, we then move on to the maximization step where we update the parameters to maximize the likelihood of the observed data. This step involves the weighted estimates, just like we showed earlier, where each point's contribution to the mean and variance depends on its responsibility for a given mode. And then once we've updated the parameters, we repeat steps 2 and 3 iteratively, computing the responsibilities and then maximizing the likelihood by finding the parameters until the algorithm converges. And so, yeah, the EM algorithm is exactly what we reasoned our way through from the k-means algorithm. And so it handles incomplete information and soft assignments effectively and still finds the optimal parameters for the model. Yeah, so, but why is this called expectation maximization? So the name reflects the two key steps that are, repeated until the algorithm converges. The E step and the N step. And they correspond to expectation and maximization. So in the E step, we're computing the expectation of the latent variables, those hidden variables that we didn't observe directly, and which in our case would be the sample assignments of the Gaussian mixture model. So in this case, that would be the responsibilities gamma, which tells us the probability that each point belongs to a particular Gaussian component. Essentially, we're calculating the expected value of the latent variable delta, given the current parameter estimates. And then in the M step, there is where we maximize the weighted log likelihood using the responsibilities we just computed. So in this step, we're updating the parameters. So that means the variances, the mixing weights, so that they maximize the likelihood of the data on the responsibilities. And then every point contributes to the parameter estimates in a weighted way based on how likely it is to each Gaussian. And so this is the maximization step because we're computing those estimates, those empirical estimates of the parameters, but those are precisely those that maximize the log likelihood. We can generalize Gaussian mixture models to handle multivariate Gaussians, which is what you see in this heat map on the right. So this plot shows the probability density for a 3-component Gaussian mixture model, where each component is a multivariate Gaussian. So instead of being confined to just one dimension, these distributions are going to have both mean vectors and covariance matrices. They're going to be parameterized by a mean vector and a covariance matrix, which allows us to capture relationships between the multiple input features. And so in this heat map, we can discern several multivariate Gaussians or several Gaussian components. So for example, this bright area here is one of the modes. And this is a second mode, and there's a third mode behind here, kind of hidden. Although it's a little bit harder to see. And so each of these Gaussians is going to have its own mean vector and its own covariance matrix. So it's going to allow the distributions to have more flexible shapes and capture both the spread and the direction of the data in multiple dimensions. And so the way this is parameterized is as a sum of multivariate Gaussian distributions. And so we're going to each component is going to have a mixing weight that determines the proportion of data points generated by each Gaussian. So for example, this bright mode here would likely have a large mixing weight, so it contributes more heavily to the overall density. And then the mixing, all of the mixing weights still need to be fall within the range of 0 and 1 and add up to 1. And so, and then to fit the parameters, you would use a modified version of the EM algorithm, similar to what we saw with the two univariate cases. Oh yeah, and in this equation here, k is the number of Gaussians in the model. So we're so each Gaussian will have its own mixing weight, parameterized by its mean vector and covariance matrix. And then the density of the Gaussian mixture model is a weighted sum over those Gaussians. All right, so to really drive home what we've been doing, we can look at how the EM algorithm works for a mixture of multivariate Gaussians. So in this first panel, this is our raw data in green. You know, we've just got a cloud of points, and you know, and then this red circle here represents our initial guess for the parameterization for the parameters of one mode. So the fact that we're seeing a perfect circle indicates that we're initially guessing an isotropic multivariate Gaussian, and then we're initially guessing a mean of 1 and -1. And then similarly, our guess for the parameters of the second mode, we're guessing an isotropic Gaussians centered at this time -1 and 1. So those are our initial guesses. And so, yeah, the means are randomly placed, and the variances are the same. We're assuming the same variance in all directions, so they're perfect circles. Okay, so our first step is to compute the responsibilities for each data point, which, as we saw, was how likely each point belonged to each mode. And in this plot, the responsibilities are shown by coloring the points. So the more blue a point is, the more likely it belongs to the blue Gaussian. The more responsibility this mode takes for having generated that point. And on the other hand, the reddish points can be more strongly attributed to having come from this mode. And then points in the middle are kind of purple, and that reflects uncertainty about which mode generated it. And so, with these responsibilities in hand, we can then update the parameters of each Gaussian using the weighted estimates. So, for example, the updated blue Gaussian, that's going to reflect the points it was most responsible for, and the same goes for the red one. And then we continue. So in the next step, we recompute the responsibilities. So that's a little bit tricky to see here, but the colors of these points are supposed to have changed slightly. And then after a few more iterations, we can see that the parameter estimates are really starting to take shape. So we're starting to shrink down. We're starting to also take on a particular shape for the Gaussian. So we can see that there's strong the two features actually covary. So this is not going to be a diagonal matrix anymore. And then after 20 iterations, we seem to have stabilized a little bit. And there's also very few purple points at this point. So the two modes take strong responsibility for the respective points. There's low uncertainty at this point about which sample came from each mode. Okay, so we hacked something together, and it happened to work. We saw it in action with two different cases. First with the univariate Gaussians, and then with the multivariate Gaussians. In both cases, this algorithm, which was loosely based on ideas from k-means, they converged and found some reasonable solutions. But now the question is like, why does this work? What's the underlying reason that this approach holds up? Even when we're dealing with missing or incomplete information. So we're next going to dive a bit deeper into the math behind the EM algorithm towards how it works in general. Um, the beauty of EM is that it's not just limited to fitting Gaussian mixtures. It's actually a general purpose framework that we can use to estimate parameters, even when some information is hidden or uncertain. And so this flexibility makes EM useful for solving a wide range of problems beyond clustering. Okay, so our goal in EM, regardless of what distribution we're trying to fit, is we want to maximize the log likelihood of the function, denoted as L theta. So formula here that sums the log of the probability density functions, which in our case is the density of the observed data yn, given the parameters theta. So yn, that's going to be our observed data, and theta is the set of parameters we're trying to estimate. And so this is the heart of the problem. We're estimating the parameters that make the observed data most likely according to our model. So that to have a picture in our heads as we go along through this analysis, the density plot on the left here is an example of what the distribution might look like for our data. So in the Gaussian case, we had our density function included a sum, and we couldn't optimize that directly. So to say that another way, our density function was a sum of Gaussians. So it was a Gaussian mixture model. It was a sum of Gaussians, and because that sum made the inside this log, it made the log likelihood difficult to maximize. And so one way to sidestep that issue of sums inside of a log is to introduce a hidden variable, z, and that's going to allow us to express the log likelihood in terms of a joint density. So not just the observed data, yn, but also including a hidden variable z. And so these hidden variables are going to capture additional unobserved information like the latent structure or group assignments in the data. And so on the bottom here, I've plotted an example of a joint density between the continuous variable y and a hidden categorical variable z. And so you can think of variable z as controlling which distribution the data comes from. So for example, if z is 0, then we're going to sample from one distribution, whereas if z is 1, then we're going to sample from the other. And so we can express the log likelihood that we had before in terms of this joint density. So recall this is how we the notation for the joint density between two variables, in this case yn and zn. And the reason why these are equivalent is because we're summing over all possible values of z. And so what happens is that when we marginalize over z, that is we sum over all possible values, we can recover the original density for the observed data. So we're summing over all values along z. to recover this marginal distribution over y. So yeah, rewriting the likelihood in this way doesn't change anything. It's just an equivalent formulation involving now one that involves the hidden variable z. All right, so y is the observed data, theta is the parameters, z is hidden variables, and then p of yn, zn given theta, that's the joint distribution of yn and zn. And then to make that computation tractable, we can next introduce what's called an auxiliary distribution over the latent variable c. And we're going to denote that q. It's sometimes called the variational distribution. And so the key idea is that we can multiply by a creative 1, specifically by multiplying and dividing by q of z. So q is the distribution over the variable z, over the hidden variable z. And then once we've rewritten the expression this way, we're free to rearrange terms. Specifically, we can choose to rearrange to emphasize the ratio of the joint distribution of p of yn, zn to the auxiliary distribution q of n. And so in this form, we've pulled out the numerator of q outside to express the rest of the fraction in terms of the ratio of q, ratio to the joint probability. So this new form is useful because we now see that we have a probability of a random variable z times some quantity, summed over all possible values of z. So what this means is that what's going on inside the brackets here, we're computing an expected value of this quantity. So we can interpret this entire expression inside the brackets as an expectation with respect to the distribution q. And that now that we have the log of an expectation with respect to the auxiliary distribution q over the latent variables, we can actually simplify things further. Specifically, Jensen's inequality is going to help us here because it tells us that because the log function is concave, the log of an expectation is greater than or equal to the expectation of the log. And so this is precisely what's shown here. And so applying Jensen's inequality is going to allow us to move this log inside the sum over z. And that's going to transform the expression into a more manageable form. So we've replaced the log of a sum which is hard to optimize, with a sum of logs, which is going to be easier to handle. And so, but then also as a result, we now have a lower bound. We now have a lower bound on the original log likelihood. So the log likelihood can never be less than the quantity on the right-hand side. And so this is neat because if we increase the function on the right-hand side, we will never decrease the function on the left-hand side. Okay, so we've established that the log likelihood is lower bounded by a new expression involving the auxiliary distribution over q. The auxiliary distribution q over the latent variable zn. And so we still want to maximize this likelihood though. And so one path forward is instead to maximize this lower bound. And so if we improve that, there's a good chance that we'll be able to improve the likelihood as well. And so we can take advantage of properties of logs to split the log of the product into a sum of two logs. So we'll first start by rearranging this part here to emphasize a ratio of p of the joint distribution over the auxiliary and the posterior and the probability of y, the marginal probability over y. And so, so yeah, we can now split it into use the property of logs. So now we've got a log of a product. Um, so this one term, and that's the second term. And so if we got a log of the product, now we can turn that into a sum of logs. And so the first term, this is actually the callback Leibler divergence between the auxiliary distribution Q and the posterior distribution of the latent variables. And so this measures how different the auxiliary distribution over the hidden variable z from the posterior distribution given the data and our current parameter estimates. And so this KL divergence that's is important because we know some things about it. Specifically, it's always non-negative, and it only equals 0 if P is equal to Q. And so the key insight here is that we want the KL divergence to be as small as possible, ideally 0, so that we're not subtracting anything away from the log likelihood. And so we can achieve that by setting Q to match the posterior distribution of the latent variables, given the observed data and the current parameter estimates. And so when we do that, the KL divergence that's going to vanish. It's going to become 0, and we're left with the log of the marginal likelihood of the observed data. And so yeah, because the inequality initially reflected the fact that using any auxiliary distribution other than the true posterior introduced a gap, the size of the KL divergence. When that gap disappears, because the auxiliary distribution is now the posterior, as we've set it, the bound is going to become tight, and that inequality turns into an equality. So once the optimal auxiliary distribution is chosen, the expression involving the KL divergence no longer contributes. And so we're left only with the log of the marginal likelihood. And that corresponds exactly to the log likelihood function we are trying to maximize. Like this is what we want. And so there's no room for the inequality to remain strict at that point, so that the two sides remain equal. And so now that we've got our log likelihood function, now all we need to do is maximize it. And this is the regular maximum likelihood estimation. So the goal is to find the parameter values to make the observed data most likely under our model. And our task is we just need to sum the log of the likelihood across all data points and find the parameter values that maximize that sum. And so, at this point, since we already computed the distributions over the latent variables, those terms become essentially constants in the M step. All right, so let's see if we can bring it all together. So this flowchart here shows the complete flow of the expectation maximization algorithm. So we kick things off by initializing parameters, which are our first guesses. And so this gives us a likelihood function with some lower bound. That's the sum of the marginal log likelihood as well as the KL divergence. And then with that in hand, we then move to the E step, where we set the auxiliary distribution over the latent variables. And specifically, we choose the auxiliary distribution to match the posterior distribution of the latent variables given the observed data and our current parameter estimates. And then when we make this choice, the KL divergence vanishes because the auxiliary distribution and the posterior now match perfectly, meaning we no longer lose anything in the optimization. And what we're left with is the log likelihood function that we want to maximize. And then at that point, we can enter the M step where we compute the parameter values that maximize the log likelihood. And so at this point, the hidden variables are no longer a concern because the E step is effectively filled in that missing information. And then with these newly optimized parameters, we can update our estimates and loop back into the E step to refine the auxiliary distributions again based on those improved parameters. And so we keep cycling between the E step and the M step, improving our parameter estimates each time until the parameters converge. And so yeah, that's how the EM algorithm works, alternating between filling in the missing data and then optimizing the parameters until we get the best possible fit for the model. And so the reason this approach works is because we're optimizing the lower bound on the likelihood function, which forces the likelihood function to improve. And so to show what I mean, the red line in the graph here is the log likelihood function, which in general is non-convex. And so we've been dealing with some multivariate cases, and so our parameters would throughout this talk we've been thinking about like a five-dimensional log likelihood surface, but in this case we've just got a one-dimensional or one parameter. So yeah, the log likelihood is red, it's concave. And then this blue line, that's a lower bound on the log likelihood that we start off with at time theta t. So this is the lower bound on the log likelihood given our current parameter estimates. And so when we select the optimal posterior distribution over the hidden variables, we're essentially figuring out where that lower bound matches the true log likelihood at the current parameter estimates. And so once we have that lower bound, we can then maximize it to get new parameters. And then with these new parameters, we can then compute a new lower bound, now represented by this green one here, by this green curve here. And then that new lower bound, we're going to maximize that, and then the process repeats. And so we keep iterating like this, bouncing back and forth between computing the lower bound and then maximizing it, gradually refining our parameters with each step. And so it's a clever approach because it allows us to tackle non-convex problems where direct optimization of the log likelihood would be difficult. And so by working with these lower bounds, we can ensure that every iteration brings us closer to at least a local maximum of the log likelihood function. One caveat of this is that if we had started very far away from the global maximum of the problem, we would get trapped in a local minimum, potentially this one right here. So that's one problem with the EM algorithm, is that it is susceptible to getting trapped in local minima. Another way to think to understand the EM algorithm is as a kind of maximization process. So this is a simplified depiction of the contours of the joint likelihood surface of the model and the latent variable parameters in the neighborhood of an optimum. And so each iteration of the EM algorithm involves two key steps. So in the E step, we're maximizing the likelihood of maximizing the likelihood with respect to the parameters of the latent data distribution, while keeping the model parameters fixed. So in this case, we're filling in the missing data, and by setting the auxiliary distribution equal to the posterior distribution for using the current parameters, we cause the KL divergence to vanish. And so this aligns the lower bound with the log likelihood function to ensure that both match at this point. And then in the M step, we shift our focus to the parameters of the model's log likelihood. And so here, with the auxiliary distribution held fixed, we maximize the lower bound with respect to the parameter vector theta, with respect to the parameters of the model. And so that gives us a new improved set of parameter estimates. And since the KL divergence is non-negative, any improvement in the lower bound guarantees an increase in the actual log likelihood. And so this iterative nature of this process ensures that at each step we're moving closer to the optimal parameters at the center here. So yeah, this is another way to think about the EM algorithm as a two-step maximization process. All right, so that brings us to the end of this lecture. So quick recap of what we did, as well as some ideas for things that you should try and go play around with on your own. So we encountered the parameterization of a Gaussian mixture model. We also talked about the label switching problem that comes up when we're trying to infer parameters of a Gaussian mixture model, and how this made the objective of MLE for a GMM non-convex. We also compared expectation maximization to a kind of generalization of MLE that can handle unobserved variables. We used various terminology for those unobserved variables, hidden variables, missing data, latent variables. Yeah, all terms that refer to the same kind of idea. We then crucially saw that EM is appropriate for certain types of problems, specifically those where there's missing data or unobserved data. And so we would want to use EM in some cases, but we don't always need to use it. There's simpler cases where MLE could do the job just fine. We spent quite a bit of time grounding the EM algorithm in terms of Lloyd's algorithm for k-means clustering. So we can draw some qualitative comparisons between Lloyd's algorithm for k-means clustering and EM. We also encountered the specific algorithm for EM in the case of a two-component Gaussian mixture model. Yeah, you should be able to go and try to implement the EM algorithm or code it up and apply it to parameter estimation for a simple GMM. We also dug pretty deeply into the math. And so we saw how to interpret the EM algorithm as, as maximizing a lower bound by alternating between eliminating the KL divergence by picking an optimal posterior distribution over the hidden variables, and and then last but not least, we also encountered the specific expressions that relate to the E step and the M step for the specific case of a GMM. So yeah, it should be well within your wheelhouse to actually go and compute specific values associated with the E step and the M step in those cases. All right. Thanks very much for your attention. We'll see you back here again next time, where we're actually going to start talking about neural networks.